Welcome everyone. As you can notice, we're going to do things a little different today. I'm at my house instead of the school, but it'll work just as well. What we're going to cover today is bivariate statistics. This is chapter 5, and it is very interesting and very important chapter. Today we're going to cover 5.A, which is the association between numerical variables. Right? So our goal today is to learn what independent and dependent variables actually are, how to create scatter diagrams, which you should already know how to do, how to find the correlation between different variables, and this is on an XY axis or a double axis, and understand the causality relationships, the different types. All right. So this is the first part of chapter 5. This is on page 102 in your book, and there are pretty much 5 sets of things we're going to do, finish with the review, and then take the test. All right. First thing, opening problem of the chapter. It says, at a junior tournament, some children each throw a discus. The things shown are your ages, 12 to 20, and the distances thrown. So what are they thrown from? About 20 to, looks like 50 meters, okay? They're all recorded. So the things I want you to think about, and we're going to do this problem later. Do you think the distance an athlete can throw is related to that person's age? Okay, just think about that. Second thing, what happens to the distance throws? So what happens when I throw, okay? And in case you guys don't know, a discus is like a big frisbee, circular disc, and you throw it, okay? Very heavy though. So what do you think happens as your age increases? What do you think happens to the distance length of throwing it? Third, how do you graph the data more clearly to see the relationship between the variables? So how can we actually graph this data given to us? And then fourth, how can we measure the relationship between the variables? So how can we measure the relationship? Our two variables here are age and distance thrown. So how can we do those two variables? All right. So just think about that, and then we're going to learn how to do all this throughout the chapter. All right. Now, in the previous chapter, chapter 4, we saw how the relationship between variables can be described using a function. Remember, we did our modeling. We did piecewise function. We did linear functions, all that stuff. In particular, in this case, we're going to consider linear relationships between the variables, okay, and discuss how they could be exact or just approximations. Now, we're going to be doing a lot of things, and the title of the chapter is bivariate data. But if you don't know what that means, this will mean nothing to you. So does anyone have a clue what that means? Well, what bivariate data is data that has two variables that are recorded for each individual, okay? So not just one, so you don't just go, okay, each individual, I record one thing for each one. No, you record two specific things for each individual, right? In most real-world situations, there will not be an exact relationship between these variables, okay? Nothing in the real world is exact. Our task is to find the model which blanks the data. What do you think? What word? Which best fits the data. And then measure how strong the relationships between the actual variables are. Okay? Got it? So, once again, what we're going to do today is we're going to start with 5.A, the association between numerical variables. Okay? And I described all the stuff we're doing. So, let us begin our lesson. So, for example, in the opening problem, there are two variables. The first variable we see is age, and the second variable, as I discussed earlier, is distance thrown. All right? So, the way this works is very simple. They're both recorded, and we expect the distance thrown to depend on the athlete's age. So we do expect some type of correlation, some relationship between the two. All right? That will depend. So age is the independent variable, and distance thrown is the dependent variable. Okay, remember, the dependent variable depends on the independent variable. So our independent variable right here, which is age, because it doesn't matter, anything can be age, that varies, is called our explanatory. Our dependent variable, pretty much the answer you get when you plug your age into your model, is our response. Okay, it's the response to plugging in our explanatory. Okay? Scatter diagram. What is a scatter diagram? Something you've been doing since pre-algebra probably. So what a scatter diagram actually is a way to observe the relationships between two variables. Now the way you guys have been doing it, and gals, is you've been doing scatter diagrams with an XY plot. Now what we're going to do is we're going to actually give the X and Y real life names and real life variables. For instance, like time and distance, okay? Age and distance thrown, stuff like that. Once again, our independent variable is always going to go on the horizontal axis, okay? So the independent variable, the variable that doesn't really matter, is our X, okay? That's the one we're plugging into the model. So horizontal axis is the one that goes left to right. What axes does our dependent variable go on? Very good. It goes on our vertical axis. That's the one that goes up and down. Okay? So you plug in X, and based on what X is, you get Y as an answer. If it was an XY variable. In the opening problem, the independent variable is age. So which one do I put that on? Do I put that on the horizontal or the vertical? Since it's independent, I put it on the horizontal. So you would pick the age on the bottom, or typically the x-axis. Now, in almost all cases, this is where age will go. This is where time will go. Those are very common types of what year you're at. Those are very common types of independent variables. Dependent, distance thrown. That is put on the vertical axis. Okay? So you'll plug in your age, you get distance thrown, and then you'll get certain plots depending on what this says. All right, that's pretty simple, isn't it? You're right, it is. See, I told you it wasn't too bad. All right. So, what I want to do first is, you have a scatter diagram. We're going to graph these data points on this graph that is given to you, okay? We graph the data value at a point of the scatter diagram. For example, the green point right here represents athlete H, who is 10 years old and threw the distance 15 meters, okay? So what I want you guys to do is plot all these. So the first one you can do is 12, 20. So 12, 20 means I would go over to 12 on the horizontal axis, and I would go up to 20 on the vertical axis. All right, so I want you guys to plot the rest of these. Okay, this is left to right, this one's up and down. Okay, I'm gonna pretend like I gave you lots of time, and I'm gonna unpause it. So let's do this. 1635. I'm just gonna touch it. 1623. All right, 1838. 13, between 12 and 14 is 13. 38. All right. 27. 19, which is all the way over here. 47. Okay. 11, 18. H, which is our 10 over 15. All right, that's a green one. 20, 50. 20, 50. 17, 33. 17, 33. See, I'm going 15 over, 22 up. All right, 13 over, 20 up. So that should have been the points that you plotted. All right, everyone here should be able to plot a scatter plot fairly simply. Now, from the general shape formed by the dots, look at the dots. You notice that as the age increases, what happens to the distance thrown? Is there a correlation there? As age increases, distance thrown does what? Correct. It also increases. See, as it goes up, it also goes up. Are there some times where your age increases and it goes down? Yeah, that's okay. All right. I haven't made one of these videos in a while, so I apologize in advance if I'm getting in the way. Correlation. You heard me use that word a bunch. Now, correlation is very, very important, especially for this lesson. The relationship or association between two numerical values, okay? There's several characteristics we can consider when describing the correlation between these two variables. Now, they are, I just listed them because I didn't feel like guessing. The direction of the graph, the linearity, okay? The strength of the graph, the outliers, are there any outliers? And then the causation. You'd be like, whoa, what do all those mean? Well, if you don't know what all those words mean, that's fine. That's why I'm here, to teach you what they mean. So the first one is direction. All right? So, positive correlation, negative correlation, or no correlation. There's three different types. So the first one's a positive correlation. This is an example of what it looks like. It's an increase in the independent variable, and it generally results in, so as I increase this, what happens to this one? As this goes this way, if it's positive, this is also increasing because it has an upward trend, okay? The graph is increasing from the left to the right. See how they're moving up? Negative correlation. So what's happening to these data points as this is increasing, it increased from the independent variable, the dependent variable is doing what? Is that an upward trend still? No, that's a downward trend. The graph is going down. So it results in the what of the dependent variable? Correct, the decrease in the dependent variable. Or value, sorry, value of the variable. All right? No correlation. What do you notice is happening here? Randomly scattered points. Is there an upward or downward trend? There is none. All right? Yeah, I could maybe say, oh, I'm going up. But then I can also say, yeah, I'm going down. So there's no upward or downward trend. You don't know what that graph is doing. It's almost going across horizontally or up vertically is the best answer. So that's no good whatsoever. Positive increases, negative decreases. No correlation is like just all over the place. And that's your direction. All right? Number 2, linearity. What word do you think of when you think of linearity? Did you say line? I hope you did. Now, what linearity is? Take a guess. Okay. When a trend exists and the points approximately form a straight line, the trend is linear. So if you form a straight line, you're linear. These points blank roughly linear. What do you think? Well, if I drew a line, does that line kind of go really close to all the points? Yeah. So they are roughly linear. Notice it's not exact. Remember what I said before. Rarely is anything exact. All right, let's look at these points right here. These points blank follow a linear trend. Do these look like they go in a straight line? No, they kind of have like a curve going through them, right? So is this linear? No. So they do not follow a linear trend. So you would say that is a non-linear trend. Non meaning no. Right? And it can also go like this. It could have no correlation. But if they kind of look like they're going up, that's linear. Right? And it's very important because when we find out what the actual graphs are, you have to know if they're linear, quadratic, maybe cubic, stuff like that. Because you have to use different programs to do each one. Strength. How strong something is. You guys strong? Maybe. So you have strong, moderate, and then weak. All right, so what strength is? That describes how closely the data follows this trend. So pretty much what it means is the closer the points are to your line, the stronger that line is. As soon as the points start to go farther away from that line, it gets moderate. And if they're really far away, like you can still kind of see a line increasing here, but it's really weak. It's like, it's almost getting to where there's no correlation. So, right here, what kind of strong do you think that is? Well, when you pretty much give the strength, you also give the direction. You like link them together. So, based on the direction, this would be a really strong, really close, right? But it's positive. It's a strong, positive correlation because it's going up. It's an upward trend. What about this one? I said moderate, right? Kind of a little farther away. Moderate positive. It's still positive. It's still increasing, but moderately. And finally, this one right here. Farther away. That is a weak positive. All right? You don't want weak positives. Yuck. Okay? TV's dirty. There we go. Get these marks out of here so you can see better. Daughter must have been messing up my TV. There we go. All right. So this one, not positive anymore. It's strong. Is it really close? A strong negative. Ah! Lost my pointer. If you guys ever notice this, you know what this is from? I couldn't find my real pointer, so I had to use this one. This is the wand from medieval time. Not medieval. Great Wolf Lodge. Magic Quest. All right. Decrease. They're kind of far away. So that's a moderate negative. And then this one, they're pretty far away. So it's a weak negative. okay? Strong positive, strong negative. Moderate positive, moderate negative, weak positive, weak negative. All depending on how close the points are. All right, we all good? Awesome. Outliers. If an outlier is the result of recording or graphing an area, it should be blank. If an outlier is generally a piece of data, it should be blank. So first off, what do you think an outlier is? Look at this. Do you see any outliers? I see only one. Outliers. Isolated points which do not follow the trend formed by the main body of data. So you have your main body of data forming a certain trend. This outlier makes no sense. Like your data is almost perfect, but you got this one point. Like, why is it there? Something messed up to put it there. So if the outlier is the result of recording or graphing error, so maybe you wrote down the wrong number, maybe you graphed it wrong, maybe there was a mistake with the machine that was calculating the stuff, you should discard it. Discard it means you take that outlier, just delete it from the data, and then recalculate everything. If it's a general piece of data, if it was true, like say, oh, this really did happen, this is something I know for a fact and there is no mistake, it should be kept. Okay, just because it's really far away and isn't like really close to the graph, if it's real data, it should be kept. So look at this one. I want you to circle any outliers you see. Go. All right, how many did you get? Only one. Here's the linear trend. Now notice, this point is really far away. This point is really far away. The rest are like all grouped back up together. This one is indeed an outlier. Why is it an outlier? Well, look how far away from our line is. Now, is this point an outlier? That's the question. This point is not an outlier. Because look, it still follows the same linear trend. It's just a lot farther away, but it's still on the same path. That's why it's not the outlier. All right. I'm going to have this whole screen clean with it in this lesson. Good? All right. Now, for the scatter diagram in the opening problem, you guys already have this graph somewhere. We could say there is a blank correlation between the distance thrown. So, using your words, strong, moderate, weak, positive, negative, I want you to say what you think this is. If you want, you can draw your line through it. So, what do you think that is? Is it strong, moderate, or weak? Strong. Fairly close. Okay, you may go, it's kind of moderate because of this one. All right, moderate, strong, more strong. Now, positive or negative? This one's definite. Definitely positive because it increases from the left to the right. The relationship appears to be blank. Is it linear or not? It is linear. It appears pretty linear. Yeah, you can go like, what if I just scoop here? Well, you have points up here, so technically you can draw a line through it. And is there any outliers? There are no outliers. All right. You may go, oh, what about these two? There's just some data that went down. That's still okay. Got it? Those just might have been weak discus throwers. Causality. Correlation between two variables that does not necessarily mean that one variable causes the other. So there could be a correlation between two things, even though the one is not dependent on the other one. Okay? Here's an example. The arm length and running speed of a sample of young children were measured. And a strong positive correlation was found between the variables. Okay? It says, this does not necessarily mean the short arms cause a reduction in running speed or that high running speed causes your arms to grow long, right? What this pretty much just means is there's a strong positive correlation between the variables because arm strength and running speed are very closely related to a third variable that was not given. And the variable is age, okay? The older that you are, the longer your arms are, right? The older you are, the faster you run. Until you get about over to your 20, then it starts going down. But anyway, they both related to age, which is, this would be my independent variable, and these are dependent on this. It just happens to be a third graph. So they're just related. It just happens to be that way. Okay. So up to a certain age, both arm length and running speed both increase because they both increase with age. All right. I just had a pen here and I lost my way. All right. Let me move on. The number of television sets sold. Let's do this one. In London, and the number of stray dogs collected in Boston were both recorded over several years. All right. Now, what happened here? It says a strong positive correlation was found between the two variables. Do you think they're related to each other? No. The number of television sets has nothing to do with the number of stray dogs collected. It's just a coincidence that they both increased over a period of time. So, there are 3 types of things I want to go over as well. The first one is a causal relationship. What that is, a change in one variable causes a change in the other variable. So when you change one variable, it causes the change in the second one. Now, there's 2 things here. The explanatory variable. That's your independent variable that explains why the dependent variable is doing what it's doing, and then your response is your dependent variable. And we discussed this in like the first slide. In cases where the causal relationship is not apparent, or we don't see it, we cannot conclude that there's a causal relationship based on the correlation alone. All right, so it doesn't necessarily just have to be on the correlation. All right. In this chapter, we're really just learning the definitions, the way things are working. We're not getting into the actual calculations yet. Because you got to know how to estimate before you know how to calculate, correct? Of course. And if you see me walking back there, I just keep on checking to make sure my video is running. I hate when I start teach this for a half hour and I realize it cut out some reason. All right, now we're going to do some examples. All right, example 1. For the scatter diagram and the relationship between 2 variables, consider the direction, positive or negative, the linearity, is it linear or nonlinear, the strength of the relationship, strong, moderate, or weak, as well as the presence of any outliers. So you're going to write 3 words down there describing the first 3, and then circle any outliers. All right? So you're going to do that for 1, A, B, C, and D, and E, and F. So I'm going to start by going over A. I would draw lines through them all. That's my line. So noticing this line, I'm going, okay, direction, that's positive. Strength of the relationship, weak, because these things are kind of far away. So I'm going to do strength of the relationship first. It's a weak, positive, linearity, linear, because it's kind of going up in a straight line. Weak, because see how far away this stuff is. And then, are there any outliers? No, I don't see any outliers. All right, continue on. Now, if you are a very strong relationship, but you have an outlier, just ignore the outlier. Pretend like it's not there. And when you're judging your relationship. Right? Continue on. B. All right, so let's see. There's my line. I'd say strong, right? We think strong. Going down, so it's negative. Definitely linear. Any outliers? Right there, there's an outlier. All right. C. All right. Ooh. What do you think about this one? This one's a trick one. Got it. No correlation whatsoever. All right. If you have no correlation, it can't be weak or strong or moderate. There's none. Can't be positive or negative. There's none. Can't be linear because there's no. Right? Can't be no outliers because they're all outliers. D. Oh. This one might got you. I have it going a little curvy here. Because if I try to go this straight, it looks like there's way too many things on top and bottom. Can't be like that. So first off, I think that's kind of strong. What do you think? Yeah. And I forget the answers here. So, okay, it's going down, so it's negative. Is it linear? No, it's non-linear. And is there any outliers? Right there, there's an outlier. Okay, Draw your line through here. That looks like a straight line, right? All right, what do you think? Moderate or weak or strong? Moderate? Moderate. There. Yes. See, I'm happy when I get the right answer too. Going up, so it's a positive. I would say linear. Any outliers? Let's finish up with that. Pop over to the other side. So you get my, I don't know if this is my good or my bad side. Actually, both my good side. Here we go. Now, let's see. Is this a straight line? I don't know. I see kind of a curvy thing, don't you? So I'm going to say, first of all, is that weak, moderate, or strong? Not strong. I'm going to go with weak because there's so many things so far away from here. It is positive because it's increasing. Definitely not linear. All right. And is there any outliers? It looks like there's a lot, but that's just because it's weak, so there are no outliers. All right. So there's my answers to my first 6 problems. All right. Tiffany is a hairdresser. The table below shows the number of hours she worked each day last week and the number of customers she has had. All right? Hours worked, number of customers. Which is the explanatory and response variables? Go. All right, just in case you forgot, explanatory is the independent. That would be hours worked. Response is the dependent. So the more hours you work, the number of customers change, right? That is your number of customers. Number 2, draw a scatter diagram. So first thing you need to know, what is my dependent is hours worked, so that goes on bottom. Okay? Now, I need to know what kind of thing to use. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That looks good. We'll just go by tens. Vertical is my dependent. That's the number of customers. 0 to 12. 1, 2, 3, 4, 5, 6, 7. So I don't got 12 lines, so I can't go up by ones, but that means I can go up by twos. 2, 4, 6, 2, 4, 6, 8, 10, 12, so on. You can fill these all in if you want. I just did every other one, just so it wasn't cluttered. All right. I want you to draw the rest of the scatter diagram. Good. All right. So 8, 9 would be 8 over, 9 up. 4, 6, 4 over, 6 up. 5, 5, 5, 5. Oops, sorry, 5, 5. 10, 12, 10, 12. 8, 7. 3, 4. And 6, 5. So now we got our scatter diagram. That one you got? Good. You got to get quick at doing those, though. You can't be too slow, or else we'll be spending forever going over this stuff. So, on which days, now we got some questions. Did Tiffany work the same number of hours? Okay, so here's hours work. So there's 2 ways to do this. You can go like this and see where you got 2 points on the same number. Boom. Or I can go, what is that at? 8. Or I can go, oh, look at number of hours, 8 and 8. So what days are those? Those would be Monday and Friday. When does she have the same number of customers? So when do you have 2 points on the same thing like this? Right there. 5 customers, it looks like. Let's see. 5 and 5. Very good. So what day would that be? That would be Wednesday and Sunday. Right? That's all there is. Explain. Why would you expect there to be a positive correlation? So as you can see, this graph has a positive, linear, pretty strong correlation. So why do you think that? Give me an answer. Type it in the chat. All right? Because that is true. We can see strong positive. The more hours you work, the more customers you should have, right? Because when you're working longer, more people come in. Therefore, you do more hair. No tricks. Pretty self-explanatory. All right. Let's move on to number 3. The scores awarded by 2 judges at an ice skating competition are shown. Okay. Judge A, Judge B. Now, are the 2 dependent on each other? Not really. In this static, so there really is no dependent-independent. they're both pretty much independent variables. And can you graph something like that? You can. Does it matter which axis you put it on? No, but they're telling you where to put them. So it says, put judge A score on the horizontal, judge B on the vertical. So label the axes and label your numbers. Okay. Judge A on the horizontals here. Let's see, they're going, lowest score is 2.5, highest is 8. 1, 2, 3. Okay, so we can go by ones. Judge B goes on the vertical, it's up and down. Once again, you can't get higher than a 10. We can go by ones. Notice this goes 1, 2, 3, 4, 5, 6. All right, I just went by twos just because it makes it a little cleaner looking, a little nicer. All right, now I want you guys to draw the scatter plot. So for instance, judge A, 5 over, 6 up, and do the other 1, 2, 3, 4, 5, 6, 7, 8. Okay, should be done. 6.57, 8, 8.5, 9, 9, 4, 5, 2.54, 7, 7.5. All right, 5, 5, 6, 7, and 3, 4.5. What happens if you get 2 points that land on the exact same spot? Is that okay? Of course it's okay. You just put them on top of each other. Okay. When you type this data in your calculator, you're not going by a graph. You're going by what the numbers in the calculator say. So therefore, it will correlate and it will change whatever numbers we need to get changed. Because eventually, we're going to plug this stuff into a calculator. You're going to come up with what this line, this linear equation, actually is. And then what some coefficients are based on that. There appears to be a blank correlation between the judge A scores and judge B scores. So draw a line and then tell me, is it going to be positive, negative? Is it going to be strong, weak, moderate? Is it going to be linear, nonlinear? All right. Strong, weak, moderate. What do you think? That looks strong, right? Strong. Positive, negative. Positive. And it is linear. Correlation between judge A score, judge B scores. This means as judge A scores increase, okay, judge B score also increase. Would it be reasonable to conclude that as you increase judge A scores, that would cause an increase in judge B scores? So does that make sense? As judge A scores go up, so would judge B's? No. Why not? Is there an equation that actually does the two? You remember what I said at the beginning? The scores are related to the quality of the skater's performances. So here's how it works. This is, I'm going to keep on saying the word wrong. Causality. All right? As judge A's scores go up, as the ice skater's performance go up, right? So those two are directly related. Judge B's scores go up as the ice skater's performance goes up. So those two are related. So it just so happens that these two are both related to the same thing, and as that thing increases, so does both of these things. It becomes almost like a logic problem, okay? Because something increases due to something else, something also increases. The two aren't necessarily related, though. Although, if judge A scores are higher, judge B scores should be higher too. They're just not dependent on each other. You don't got a independent-dependent relationship. Got it? No response. There is no response. All right, number 4. Paul owns a company which installs industrial air conditioning. The table shows the number of workers at the company last 10 jobs and the time it took them to complete said jobs. Which job took the longest? All right, so the longest job is the job that took the most number of hours. So look up there. Which one? You got it? What number's the biggest? 10. What job is that? Job G. This stuff's like middle school stuff. Actually, my 3rd grade daughter could probably do this. Which one involved the most workers? 4? No. 8. 8 is job C. Draw a scatter diagram to display the data. Okay, typically the one on top is your independent variable. So that's where your number of workers goes. 0 to 10. Time, 0 to 10. Okay, so actually the time changes based on how many workers. The more workers you have, the less time a job should take. I give you the answer. All right, here we go. Let's plot some points. 5 over 4 up. 3, 6, 8, 2.5. 2, 9. 5, 3. 6, 4. 110. 4, 4. 2, 7.5. And 7, 3. Now, is there a relationship here? I see one. It's not really necessarily linear. Kind of levels out. The reason it levels out is you're never going to really have 0 workers working. All right? And jobs will never only take 8 hours. It could take forever eventually. Now, so if you had 50 workers, eventually what happens is your workers get in each other's way and they're just not going to go any faster. That's what this means. All right, so describe relationship. So what's this graph doing? Decreasing. And all these points are pretty close to my line, right? So I would say it's a strong, negative, nonlinear correlation. Okay? And as I said before, what this is telling us is the more workers you have, the less time your job should take. Does that make sense? I think so. All right. Make sure you got that all. And let's go to number 5. We only have 3 more, 5, 6, and 7. All right. Choose the scatter diagram which would best illustrate the relationship between the 2 following variables. All right. The first one says, a number of apples being bought by customers. Y is the total cost of apples being bought. B, the number of push-ups a student can perform 1 minute versus the time taken for the students to run 100 meters. C, the height of a person versus the weight of a person. And D, the distance the student travels to school and the height of the student's uncle. Ooh, that's an interesting one. So first one, number of apples bought by customers, the total cost of apples bought. So what usually happens to the cost per something, the more you buy. So think of Costco, or think of, you guys have Costco, or BJ's, okay? Those stores sell things in bulk. Because they sell things in bulk, the cost of all that stuff you're buying is actually cheaper. So the more apples you bought, the total cost of the apples is what? It decreases. So you should have, number of apples bought. Oh, total cost. So everything I just told you is a lie. If it was per apple, it would be decreasing. But because you're buying more apples, the total cost bought increases, right? Because the more of something you buy, the more it costs. All right, so that could either be B or D. Do you think it's pretty straightforward, or do you think it's kind of all over the place? What do you think? I'm going to go with D. Why D? Well, because it's priced per apple. Okay, you usually pay per pound, right? And all apples weigh about the same. So therefore, each apple costs about the same amount of money. So every apple you add on goes up about the same height. So it's going to be a nice tight, it's going to be a strong linear correlation. Push-ups and time it takes them to run 100 meters. All right. Now, the more push-ups you can do, what does that probably mean? It means you're pretty strong, you're pretty athletic, right? So if you're more athletic, what does that mean with your 100 meters? Do you think it goes up or down? Down. So you think it's that's true. So the stronger you are, the faster you run. So as you do more push-ups, your time goes down, meaning you're faster. And that would be letter A. Height of a person versus the weight. The taller someone is, usually the heavier they are, right? Now, this one varies a lot because people can be overweight. I got a little belly on me. Or they can be really skinny. That was me in high school and college. All right, so my weight would probably be around here. In high school and college, I was down here because I was wrestling and way underweight. Now I'm old and eat too much, so now I'm way overweight, so I'd be up here. But I should be over here. So it goes more moderate weight correlation. It would be B. See, using me as a nice thing. So if I start exercising, hopefully, get back to there. Distance as a student travels to school and the height of their uncle. So the farther away from school you are, typically the taller your uncle is, right? No, not at all. It doesn't have anything to do with each other. There's no correlation whatsoever. The answer is C. All right. 2 more questions. Number 6. This is a good one. Scatter diagram shows the marks obtained by a student on a test out of 50 marks. This is like a IB. So these say marks. Marks is the same as like 60 points. All right. Plotted against the number of hours each student actually studied for the test. So what happens the more you study typically? Oh, I made this question on the last test. The higher your test grade is, right? So what's the correlation between these variables? So let's draw a line through them. What do you think? Give me some words. Strong or moderate? I'm going to go moderate, I think. Moderate. There you go. Positive or negative? Positive. Linear or non-linear? Linear. All right, that's pretty good. So pretty much as the number of hours you study goes up, the higher your marks are. So it's moderate, positive linear correlation between the hours of study and the marks obtained. How should this outlier, this little guy up here, how should he be treated? Someone only studied 4 hours and they got, how'd they get above a 50? Well, they got above a 50. How should I be treated? The test is out of 50 marks. So you really can't get above a 50, can you? So it's probably an error. The teacher messed up. They was probably more closer, instead of 57, it was probably closer to like 27 or maybe even 37. So they messed up their number. So what should we do with the outlier? Throw it out. Just discard it. So you'll take this away, and when you actually find your graph, you're going to use every point but this one. You'll delete that data. Do you think there is a causal relationship between the variables? What do you think? Yes, there is a causal relationship. You know why? Well, spending more time studying, the more you study, is likely to cause a higher test mark, right? Because you guys, the longer you study, that's why you study a lot before a test, right? Before all your tests. Please. Well, you get high test scores, so I assume you do. So that's good. All right. Ready for the last question? So, when the following pairs of variables were measured, a strong positive correlation was found between each pair. Discuss whether there is a causal relationship exists between the variables. If not, suggest a third variable that they're both related to. Okay. Now, ready? The length of one's left and right feet. Now, you would say, why doesn't it say left and right foot? Well, once again, it says feet because this is a international baccalaureate book. So, is there a strong positive correlation? What do you think? Not causal. What is one's left and right feet related to? Dependent on your genetics and age. Okay, it's not necessarily my left foot. Depends on how big my right foot is. Depending on just your parents or your lineage and how old you are, that's how big your feet typically are. And then your left and right foot are typically the same size. Okay? Damage caused by a fire and the number of firefighters who attend it. What do you think? Are those directly related? No. Why not? What are they dependent on? Dependent on the size and location of a fire. Okay? You could have 100 firefighters turn up to my tiny little house and my house be burned, or them save my whole house. You could have 100 firefighters turn up to Linden High School and then just a little piece of Linden High School be burnt down, but more is gone. Okay, so depending on how large it is, and depending on the location. A fire in like a refinery, you have to back up and you can't go up there because what happens is really dangerous and it puts the firefighters at risk. And their main goal is to save lives. Their secondary goal is to save damage to equipment and stuff. Companies' expenditure, how much they spend on advertising, and the sales they make the following year. So do you think the amount they spend on advertising directly affects how much they make the following year? Casual. Of course it does. The more you spend on advertising, the more you make. That's why companies spend millions of dollars on ads at the Super Bowl. Height of the parents and the heights of their adult children. Is that a direct relationship, do you think? I'm sorry. An increase in advertising causes the increase in sales. I just said that. That is also casual. What do you think? Where did I sit up here? Genetics. Children's adult height is determined by the genetics they receive from their parents. One gives you an X chromosome, one gives you a Y chromosome. That has all the DNA you need in it. Merges together, and typically you guys are a mixture of the two. You're not, and in some occurrences, you see someone that's like 7 foot tall that had 2 little short parents, or someone that's really short that had 2 large parents. But typically also with brothers and sisters, they're all around the same height. The brothers are and the sisters are. Girls are typically a little smaller. Not all the time. Number of hotels and the number of service stations in a rural town. What do you think? Not casual. But what can relate the two? How about they're dependent on the population of the town? The more people you have in a town, the more number of hotels you need. And then the more people you have in town, the more number of service stations or gas stations you would need as well. Okay. And with that, we are going to, what do you think? Conclude my first lesson at home. Hopefully this is the only one I have to do here. This is the bivariate statistics, association between numerical values. So this gave you all the words you needed. And the key words that we got from today is positive up, negative down, nor correlation. Doesn't mean anything. Okay. If it's a lot of points tight to the graph, it's strong. If they're a little bit away, it's moderate. If they're really far away, it's weak. And then if it creates a straight line, it's linear. If it doesn't, it's nonlinear. All right? Casual, it means it's a direct relationship between the two variables. Non-casual means you have to link them through something else to link them to each other. All right? That is everything. Isn't that awesome? So, till the next time, have a good day. Study up.